I'll be talking about building and training basic neural networks. So first, we'll try to discuss on that neural networks are basically built up using tensors. So we'll talk about how you can convert the different data types you have to tensors. So that's using encoders. And once you have the tensors, how will you convert them back to the initial data type you started with? So those are decoders. Finally, when you have the data in form of tensors, you need these layers, and then you need the constructors to stack these layers up and create your own neural network. Finally, once the neural network is built, you need to train these. So we'll see what are the different options in training these networks and what are the different loss layers which are involved while training these neural networks. We'll talk about two examples. The first is performing a logistic regression for classification using real-world data. Again, we'll use the example data which Etienne had pointed to. And then we will train the Loo network on handwritten digits, which is basically the hello world for image classification for deep learning. So for each of these, we will see what layers are involved in the network, how to construct them, and then finally we'll see how good the network has performed. So first, as I said, neural networks are created with tensors. So for the purpose of neural networks, tensors are just multidimensional arrays, so they can be scalars, that's single input, vectors, so that's a list of inputs, matrices, which are two-dimensional arrays, so those are lists of lists, and then you can have rank n tensors, which are lists of lists of lists, and so forth. So let's go ahead and see examples of tensors in real world. So vectors are two-dimensional or a single-dimensional tensor, rank 1 tensor, is used as a coordinate of points. Matrices, which are lists of lists, so those can be transformed. So this is just a row matrix. So that's a disk matrix which is converted into a grayscale image. Finally, you can have rank 3 tensors. So those correspond to the 3 RGB channel frames in RGB image. So now that we know that tensors are essentially, so your images can be converted to tensors, let's go ahead and see how do we do that. So network data, so that's done in that are converted into tensors using encoders. So there are different kind of encoders that you can use in the Wolfram language. One of them is class encoders that we will deal with. So here we are creating a class encoder. The two classes are male and female, so we created a net encoder. A thing to note that the output here is of range 2, and then we encode the input we have. So these are just males and a list of males and females. We encode that using the net encoder here to create this list, which is nothing but a tensor. So finally, at the end of the neural network, we'll have again a list, a numerical list like this. We need to feed that back into a decoder to get back the actual classes, which is male or female. So a thing to note that the dimensions of the decoder, the dimensions of the input that you feed into the decoder should be same as the index which you had created in the net encoder. So here, when we are putting this list, it should be two-dimensional, so we get it's finally converted back into the class that we started with. Similar to class encoders, we have image encoders. We will give the input in a similar way. So we put net encoder, that's the Wolfram language function. We say that this is an image encoder. We give the dimensions of the image, and the color space is additional option which you can add to it. So here I'm using a grayscale image, hence I put the color space as grayscale, which means that the color channel is just one. So we feed this image into the encoder, so that's the encoded image. Finally, we can feed the encoded image into a decoder, which we can create in a similar fashion. So this is the image decoder created with the grayscale color space. We can feed the decoded image into the decoder to finally get back the image which we started with. So let's go ahead and see the different layers which are present in the Wolfram language. So here is the table of all the layers which we have till 11.1. So the first three are the basic layers, and the second are the element-wise computation layers. So these are the type of layers and the corresponding layers that we have in the Wolfram language. We will go ahead and describe a few of these layers, the layers that we will use in the networks that we will train. So once we have the layers, we need to put them together. So net chain is the function that would help you in stacking the layers one after the other, so in a chain-like fashion, to create this neural net. So here I'm just using the net chain to put together a linear layer and a logistic sigmoid layer, or element-wise layer, which has the function logistic sigmoid. So you see that once net chain is used, you see I am putting the input into the linear layer and then finally to the logistic sigmoid layer, and it shows here uninitialized, which means that this chain has not been initialized yet. So if we have to have more complicated structure, we need something which is more than a chain. So for graphical neural networks, we use net graph. So here we have combined or put together ramp and logistic sigmoid, finally catenated them together. So we catenated the inputs from the ramp and sigmoid, and that is shown by this 3 yellow, which is the catenate layer. For net graph, you need to provide the connection. So here 1 is connected to 2, and then 1 and 2 are separately connected to 3. So for the other constructor which we have is net port. If you have multiple inputs or multiple outputs, you need to label, or you need to label these ports of input and output. That is done using net port. So here net port is used to specify that the first input comes from this input 1, and then that's connected to the ramp, and then input 2 is connected to the logistic sigmoid. So whatever you feed in input 1, the ramp function will be applied to it, and for whatever you put into input 2, the logistic sigmoid will be applied to it, and then finally you'll get the total of these applied functions, and that would be fed into the output. So these are the constructors for the neural networks. Finally, when you have created your neural network, you need to train it. So what we had seen till now is that neural networks are basically created on tensors, so they are just data-driven algorithms. And when you are training it, you are trying to find a function, and when in the process of training, you are tuning this net to approximate this function. While training, you are finding this local optimum for the loss, which is as a function of the learned parameters you have. So to train one parameter, you have the error or the loss function that is computed for the batches of this training data. And then it's backpropagated, the error is backpropagated through the network. Updating the parameter is done through different variants of gradient descent. So here is a function, here is just a visualization of what happens when you are actually training a neural network. So you're just trying to minimize this cost function, or trying to minimize the error with regards to the different parameters you have. So a crucial part for training this neural network is to specify the loss function that you are minimizing while training. So there are different types of loss functions in the Wolfram language. These are the inbuilt ones. You can definitely add your own loss functions. So the inbuilt ones are, the first one is the mean absolute loss layer. So that's the Poisson type. It's generally used for regression problem. So you just take the difference between the target, the input and the target. So the absolute difference between the two, and then have an average of them. So this is essentially the functional form of the mean absolute loss layer. So you see that whether I apply the function or the loss layer, I get the same result when using the data which we provided. Similar to mean absolute loss layer, we have mean squared loss layer. So you just take the Gaussian type loss for this. So you take the square of the difference between the input and the target. And similar to the above treatment, we have gotten the functional form of this loss layer and see that the mean squared loss layer is just the same as the functional form. The third is the cross entropy loss layer. So it's an information theoretic distance which compares the probabilities of the input and the target. So essentially, this is the function that's used to compute the cross entropy loss layer for the probabilities. So here the input and the target are a bunch of probabilities. That's a typo here. So these are just a bunch of probabilities. And this is generally used after a softmax layer or a logistic sigmoid, which gives its output in form of probabilities. So when a loss layer is not specified, Wolfram language will automatically choose this depending upon the layer you are using it. So for softmax and sigmoid, cross entropy loss layer will be used, and for all other layers, mean squared loss layer will be used. And if you've provided a specific loss layer yourself, so that will be used. So now we'll go to actually doing a real world example. But before that, as we said, that we'll describe a few of the basic layers. So a linear layer is essentially an affine transformation. So you have the data and you multiply it with this weight matrix and add a bias to it. These layers have a lot of parameters, and they are generally used towards the end of the network after a downsampling has been done. So to understand what a linear layer does, let's first define a linear layer. So it has a three-dimensional input, and it will have a two-dimensional output here. So 2 output and 3 input. So we first initialize the layer. Once we initialize the layer, we can extract the weights as well as the biases from the layer which we initialized. So this is the way, so net extract is the function which you use to get the weights and the biases weights and the biases in this layer. So you can get any parameters for the corresponding layer. Here the parameters are in the form of weights and biases. So once you get the weights and the biases, you can put it in the functional form. So that's the dot product of the weight and the data which you have, and add the bias to get the same answer that you would have gotten if you had just used the linear layer. We have the element-wise layer that would apply a unary function to every element. So the element-wise layers, the activation functions which are mostly used are logistic sigmoid tan H and the rectified linear unit. So here we have those. You can use it with the element-wise layer, or if you just specify tan H, that also signifies that you are using the element-wise layer here. So I'm taking the data, I'm just applying the element-wise layer tan age. So the answer which I get is just the same as you would get if you just apply tan age to the data. The third layer which we'll be using in this regression analysis is that a softmax layer. So it returns a normalized class probability. So each of the element is converted into this particular expression. So that's a probabilistic interpretation of these vector which it's supplied. So I'm taking a data of 10 random numbers, and I'm just applying the softmax layer to these random numbers, and what I will see is the answer which I receive while applying the softmax layer is just the same as as I would receive when going through the functional approach of putting this function to each number in which is entered into the softmax layer. So now we know what layers which we are using to classify this logistic regression. To classify using, so we'll perform a logistic regression. We'll take the Titanic data set, which is again there in the example data or in the data repository which we have. So there we'll take 800 of these example data as our training set, and we'll keep the remaining as our test data. So that's what the function take drop is doing on these data set. First, we make sure that we have cleaned all the missing data from in this data set. So we finally see that there are 800 in the training data and there are around 246 in the test data set. So the data set, we see that it has a class. So which class the passenger was traveling, the age of the passenger, the gender of the passenger, and finally it gives the result which says whether he or she has survived or not. So that's a Boolean output which we have for this particular data set. So what we need to do is to we convert these classes and the gender into their appropriate vector. So we need to use the class encoders and gender encoders. So we'll use the class encoder which we had seen previously. So now we have 3 classes, and then we have 2 genders, so male and female. So we create the corresponding encoders. So now that we have created the encoders, we need to concatenate all the input, the 3 input which we get from the class, the gender, and the age. So we concatenate all of these input together, and so this is the first step of concatenating the input. Next, we will connect it to the actual layers that perform the logistic regression. So those would be the linear layer, which we had seen previously, and the logistic sigmoid. A thing to notice that element-wise layer logistic sigmoid is same as logistic sigmoid, putting logistic sigmoid in the net graph or a net chain. So once we have connected these layers, we have to finally connect it to the net port, which gives the output. So the output is again a Boolean decoder, which we had true and false, denoting if the passenger survived or not. So we create the net for this particular regression. Then finally, we'll train this network. So we take the net which we had created, we train it on the training data, the first 800 examples which we got from the data repository, and then we use an option that shows the number of times we want to use this training data. So we say that each of these data will be used 1,000 times. So this is how we train this data. And then finally, when we have the trained network, we will check to see if to check if fictitious passengers whose properties we will specify whether they have survived or not, and what's the probability of their survival. So the first passenger which we say is that the passenger was traveling in first class, 20 years, and she is a female. So we need to check if this passenger survived and what's the probability of their survival. Second is a male traveling in third class, 30 years of age. So we see that the female had quite a high chance of surviving, and the male unfortunately did not have a large chance of surviving. So essentially he died. So we take the probability, we find out the plots for each of these gender and class separately, so we can create plots like this. So we see that the female traveling in first class had pretty high chance of surviving. Younger tend to have a larger chance of surviving. So a good thing to see is or a good thing is that we can put this trained network in the classifier measurement as Etienne has said, so we can convert them to the classifier measurement object and find out and get the different properties which classifier measurement objects has. So here we are just trying to find out how accurate it is. So we get around 81% accuracy here. We can do a similar kind of analysis using the inbuilt classify function which we had. So, and we get similar accuracy as to the inbuilt classify function that we have. So the final example is the NuNet, which is trained on the handwritten digits. So the different blocks in this particular neural network is as it's seen, is that we have the first convolution block, then a pooling block, then another convolution followed by pooling, and then finally we will convert these into a probability. So first we have fully connected blocks. There are two fully connected blocks, and in each we finally reduce the dimensions, and at the end we have the 10 dimensions that corresponds to 0 to 9 of handwritten digits. We convert it into the probabilistic interpretation by putting a softmax layer to it. So let's go ahead and get the training data. Again, we have them in the resource data, and this is given as a resource object of the MNIST data. So we are training it on the handwritten digits from the MNIST database. So first, let's go get them. It's given as training data and test data in the database. So we obtain these objects, resource objects, or we obtain the data. Next, we use the same net chain. We use the same network using net chain. We put them all together, the different blocks of convolution pooling along with the fully connected blocks, and then the input is an image. So as we had seen for image encoders, they are grayscale images. So I'm just putting the color function as grayscale here. And the output is the class. So that goes from the handwritten digits, which go from 0 to 9 here. So once we have constructed this network, we can train it on the training data. So I'm not going to train these the first two examples here. So here we are just letting Wolfram Language determine the different options of the net train. So if I do this, you'll see that it takes more than 40 minutes to do this particular training. So how do we improve this? A good thing to note is that if we had done this, it would have gone to a max training round of around 10. So we don't need all of those 10 rounds. We'll see that the loss eventually plateaus, and we don't need all of those 10. I'm just stopping it. So while training a network, you can stop it at any point, and you can use whatever is trained to get your results out of it. So here we see that max training round of 2 would be enough. Another way to improve the speed is to increase the batch size. So I'm putting the batch size to 512 here. This, in fact, increases the inputs per second. You see this, it increases this input per second time if you increase the batch size. By default, the batch size is determined by the size of your data and the size available. The maximum batch size which is set to is 256. Again, I'm just using a higher batch size here to optimize it, do it in a faster way. And what so still I see that it would take around 8 minutes to complete that computation. To go and train it faster, I can put a target device here, and if I put the target device to GPU, I see that it just finishes in around 30 seconds. So once I have the trained network, I can, again, as we had seen before, put it into the classifier measurements to get the classifier measurement object and get the different properties which we get from a classifier measurement object. So here, let's go ahead and see the confusion matrix plot. So in a confusion matrix plot, the more the diagonal is populated, the better our accuracy is. So we see that there are a few occasional misclassified samples. As Etienne had talked about, all the different properties that you can get from these classifier measurement, you can see which are the most the best classified or the worst classified examples. Finally, let's go ahead and see how accurately our network had performed. So we see that there is around 98% accuracy. You can get other different properties while training the network. So here in this example, I got the loss evolution, so how the loss and the weights and the gradients have evolved during the training. It's good to see the corresponding correspondence between the two. So I see that once the loss has plateaued, which means the biases and the weights have sort of plateaued too. So once you have your network, once you have trained your network, you can export it. So use the WLNet extension for exporting the network. So I'm just exporting the network here, and then you can again get the pre-trained network by simply importing your file. And similarly, you can do the further analysis of the network by just importing a pre-trained network. So that was more or less a brief introduction to the basic neural networks in the Wolfram language. Sebastian will continue talking about recurrent neural networks and other features which we have.